This is the first section of chapter 8, which is all about modelling with differential equations, and this section is modelling with first order differential equations. Now you'll know from core 2 that if you want to solve a differential equation, then we've learnt the method of using the integrating factor. Now from pure 2, you would have learnt the separation of variables, but I would imagine, since you are doing a core 2 exam and you get a modelling question with a first order differential equation, it's going to be using the integrating factor. So just a reminder of the integrating factor. It's when we have a first order differential equation written in this form, so dy dx plus some sort of function of x, y equals a different function of x, and the integrating factor, let's just call it the if. You get this by doing e to the power of the integral of px dx. Now just be aware that with a modelling question we often have things with respect to time. So let's say, for example, that it was volume that we had with respect to time. So our differential equation might look something like this. If it was volume with respect to time, then you may see something like this, where V might be volume. So just be aware that you've got different letters and you need to be prepared to sort of take what we're used to and match up the letters for x and y with these. So x, 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 t, 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 y, y, v, v. Okay, so that's the only thing you need to watch out for. Okay, so here a particle starts from rest at point 0, which is the origin. So if it starts from rest, so rest means t is 0, the origin is s equals 0, and this all happens when t is 0, because that's when it starts, and it moves along a straight line. At time t seconds, the acceleration is given by this expression here. So we've got the acceleration, find the velocity. So just as a reminder, when we differentiate the displacement with respect to time, we get the velocity. When we differentiate the velocity with respect to time, we get the acceleration. When we integrate the acceleration with respect to time, we get the velocity plus c, let's call that c1. And when we integrate the velocity with respect to time, we get the displacement plus a different constant, we'll call that c2. So that's just a reminder of variable acceleration, which is what we've got. So let's start part A. So if we want to find a velocity of p at t seconds, then the velocity is equal to what we get when we integrate the acceleration with respect to time. So that's going to be equal to integrating 6 over t plus 2 squared dt. So let's write the power as t plus 2 to the negative 2 dt. We'll move the constant over just to make it slightly easier, like this, and then we can use the reverse chain rule to integrate what's here. So we add 1 to the power, divide by the new power, so we integrate the outside. So that would give us negative t plus 2 to the power negative 1. Then we times by the inside integrate differentiate, which is just 1. So we just get this plus c, which is what v is. So let's tidy that up. So we've got negative 6 t, actually let's write it as v equals negative 6 over t plus 2 plus c. So now we're going to work out c, and we can work out c using the information that's here. So we know that when t is 0, v is 0. So let's write that down. T is 0, v equals 0. So we'll substitute those in to find c. So that'll give us 0 equals negative 6 over 0 plus 2 plus c. So that just gives us there that c equals, that's going to be 3. C equals 3. So our final expression for v is going to be negative 6 over t plus 2 plus 3, and that is meters per second as it's a velocity. So let's just highlight that before we move on. Okay, and what I'm going to do, I'm going to call these constants here C1, as I'm going to be using another constant in part B, and I don't want there to be any confusion. So part B, show that the displacement of P from O when T is 6 is given by that. So if we want to find a displacement, we want to find S, it means we integrate the velocity and we're going to get a constant there. So the displacement S is given by integrating the velocity with respect to time. So S is going to equal integrating negative 6 over t plus 2 plus 3 with respect to t, and we'll do that down here. Now for this part here, when we integrate it, I'm going to do log of the bottom. So if I did log of the bottom, that would give me 1 over t plus 2. So I've got to times it by negative 6. So the first term integrated becomes negative 6 log t plus 2, and the 3 will just become 3t plus c. Okay, so this is what S equals. I've been given some initial information back at the top again. When S is 0, t is 0, and I'll substitute that in so that I can find c. So that will give me, let's start with S. So 0 equals negative 6 log 0 plus 2 plus 3 times 0 plus c. So from that, let's see, what do we get for c? That will cancel out. This will give me negative 6 log 2. So if I bring it over to the other side, it will be 6 log 2. So my full expression for S is negative 6 log, not sure why I'm putting brackets in, negative 6 log t plus 2 plus 3t plus 6 log 2. Now there's no point trying to simplify that, because I'm now going to substitute in t equals 6. So let's put t equals 6 here. So s equals negative 6 log 6 plus 2 plus 3 times 6 plus 6 log 2. So from there, this will just become negative 6 log 8 plus 18 plus 6 log 2. Now 8 is the same as 2 cubed. So what I can do is write this as log 2 and times by 3 here. So I get negative 18 log 2. It's the same thing. So I have s equals negative 18 log 2 plus 6 log 2 plus 18. Then that will give me the form required, because now I can put these together because they're both log 2. So I'll end up with s equals 18 plus or minus 12 log 2. So s equals 18 minus 12 log 2 as required. Okay, so we've got a particle that's moving along a straight line. At time t seconds, the acceleration is given by this expression here. Given that when v is 0, when t is 2, show that the velocity of the particle at time t is given by this equation, where we need to find the value of this constant, c. Now, if we look at this, we know that if we want to find the velocity, that's what we get when we integrate the acceleration with respect to time. So another way of saying that is that dv dt equals a. Now, the way this equation looks at the moment, or this formula looks at the moment, we can't solve it because we've got t as a variable, we've got v as a variable, and we've got a as a variable. We need to eliminate at least one of those, and we can eliminate the a, well, not really eliminate it, but change a to dv dt, yeah, because we can't deal with something with 3 different variables. So a I'm going to write as, so if I write since a equals dv dt, then I can write dv dt equals t plus 3 over t v. Okay, that's step number 1. Now you might look at this and you might think, okay, let's try separation of variables to solve this. Well, you can't do it because you're not going to be able to get the t isolated from the v. Yeah, it doesn't matter how you try factorising, it's not going to work. And because this is core 2, this is going to be another method other than what we'd use in pure 2, separation of variables. So the method we know is about the integrating factor. Now if we were to write down when we use the integrating factor, so that's when we've got dy dx plus a function of x times by y equals a different function of x. You'll notice that this looks a bit like this. Now we haven't got x's and y's, we've got v's and t's. So let's write this using v and using t. So it'd be dv dt plus, well, it'd be a function of t times by v equals a different function of t. And it does sort of match up with this if I rearrange it. And to solve this, I would use the integrating factor. Well, from here, the integrating factor would be when you do e to the integral of px dx. So here the integrating factor is going to be pt dt. So it's important to sort of get letters to match up. So step number 1, let us now, or step number 2 or 3, get it to match up. So we'll rearrange it. So we'll write dv dt minus 3 over t v equals t. And we're going to solve by using the integrating factor, as we've just spoken about. And the integrating factor is going to be, e to the integral of pt. Now pt is this minus 3t. So it'll be minus 3t dt. Now I can take the minus 3 over as a factor. So it just leaves me 1 over t dt, which is easy. So now I get e to the minus 3 log t. Now if I move the negative 3 over, so it's a power, like this, then the e and the log cancel out, just leaving me with t to the power negative 3. That's my integrating factor. So now I times all the terms in the original equation, differential equation, first order differential equation, multiply every term by t to the minus 3. So that will give me t to the minus 3 dv dt minus t to the minus 3 times by 3t, or 3 over tv, equals t to the minus 3 times by t. Now we need to remember that this is the result of differentiating a product, and that product is going to have this part. So this is where you'd always find u, that part of the product, and this is where you're going to find the other part of the product, v, here. Yeah, now I'll just change the form that it's written in here just to make that a little bit clearer. So t to the minus 3 dv dt. Now if I look at this part and take that t here, this will actually become t to the power negative 4. So I'll have negative 3 t to the negative 4 v equals, and then the other side over here will just become t to the power negative 2. So hopefully you can see more clearly here the result of differentiating a product, because if that's u, this part is what u dash would be. Yeah, so that differentiating becomes this, and then the v differentiate just becomes 1. That's why there's nothing here. So the left hand side will write that it's the result of differentiating with respect to t, this product, t to the minus 3v, that's equal to t to the minus 2, We now integrate both sides. So we will have this t to the minus 3 v dt equals the integral of t to the minus 2 dt. These cancel out here, so that just leaves t to the minus 3v equals what we get when we differentiate this. So, when we integrate this, so that will become minus t to the minus 1 plus c, and now we're going to work out what c is, and we can do that using this. When v is 0, t is 2. So let's just substitute in v is 0 and t as 2. So we will get 2 to the negative 3 times by 0 equals negative 2 to the minus 1 plus c. So that becomes 0. This is minus a half, so that means that c must be equal to a half. So our final answer is going to be that v equals negative t squared plus half t cubed. Now the reason I've ended up with that is because I've basically taken the expression from above here, and if you times everything by t cubes, you'll get the expression in the form that they want, because you'll notice there's no negative powers here. So if I times everything by t cubed, that becomes v. This becomes negative t squared, and this will become c times by t cubed, which is what I've got there. So yet again, we've proved it as required, and we found the value of c. So we might want to probably just say at the bottom here that c is a half, so it's part of our answer as well. I'll just highlight that. Okay, so we've got a storage tank here. Initially contains 1,000 litres of pure water. Liquid is removed from the tank, so it's removed at a constant rate of 30 litres per hour, and a chemical solution is added to the tank at a constant rate, so added at a constant rate of 40 litres per hour. The chemical solution contains 4 grams of copper sulfate per litre of water. Given that there are X grams of copper sulfate in the tank after T hours, and that the copper sulfate immediately disperses throughout the tank on entry, show that this situation can be modelled by the differential equation that we're given here. Right, so first things, chemical symbol for copper sulfate, although not really needed for the question, but it will just shorten some of the writing I need to do. CuSO4. So a quick Google allowed me to find that, because I couldn't remember from my A-level chemistry many years ago what it was, and also a little drawing of what's going on. So I've got some sort of tank here that's got chemicals in it, or chemical being poured into it like this. So it's already got 1,000 litres of water in it, of pure water. Yeah, so there's 1,000 litres of pure water as opposed to impure water. Then we've got liquid being poured in. So let's do like a little cup here. and liquid is being poured into the tank, and it's being added to the tank at a constant rate of 40 litres per hour. So 40 litres per hour. But water is also removed from the tank. So let's say there's a little tap on the side here, and water's sort of removed from the tank. So let's do some like drips there going down, and it's being removed at a rate of 30 litres per hour. So 30 litres per hour. And the water that's being poured in has 4 grams per litre of copper sulfate. So 4 grams per litre of CuSO4, our copper sulfate. Okay, so the diagram's not really necessary, but helping, if we've got that just helps in terms of answering the question if we can visualise what's going on. Right, so the first thing I want to do is to work out the amount of liquid in the tank. Amount of liquid in the tank after T hours. Now, what have we got? Well, we've got 1,000 litres already there. And the amount of liquid, that's going to be in litres. Then we've got 40 litres per hour going in and 30 litres per hour taken out. So overall, we're going to have 1,000 plus 10t litres in the tank after T hours. So you can see that every hour what's going to happen, you're going to get an increase of 10 litres. So we'll start with 1,000 litres. After an hour there'll be 1,010, 2 hours 1,020, and so on. Now, as the amount of liquid in the container changes, the concentration of the copper sulfate will change. Now, it's not going to be like a simple linear thing because copper sulfate is being added. So you're having copper sulfate being added. Some copper sulfate is going to be lost as it's taken out. So it may be that the concentration increases or it decreases. And this is what this differential equation is. It's about the concentration, which is X. X is like the concentration of copper sulfate over time. So what we need to do is to work out, well, what is the concentration of copper sulfate in the tank? Well, that's going to be equal to the amount of copper sulfate in the tank, amount of copper sulfate in tank, divided by the amount of liquid in the tank, amount of liquid in tank. So the amount of copper sulfate in the tank is given by X, the amount of liquid in the tank is given by 1,000 plus 10t. Now, that concentration will change as copper sulfate goes in, and some copper sulfate comes out with this 30 litres that comes out every hour. So if we look at the copper sulfate that goes into the tank every hour, so there's 4 grams in 40 litres, 4 grams per litre. So the amount of copper sulfate that goes in per hour is going to be 4 times 40, so 160 grams of copper sulfate in per hour. How about the copper sulfate that's coming out? Well, that will be whatever the current concentration of copper sulfate is per litre times by 30, because there's 30 litres coming out per hour. So we need to times this by 30. So that's the concentration of copper sulfate in grams per litre. And we've got 30 litres, so we need to times it by 30. So we're going to have 30 times by x over 100 or 1000 plus 10t. So cancelling down, that will give 3x over 100 plus t grams per hour. So the change in the copper sulfate in the tank over time is the amount of copper sulfate that goes in grams per hour, which is 160. Take away the copper sulfate that comes out per hour, which is 3x over 100 plus t. So that's our differential equation proved as required. So now we'll move on to part B. Part B says, hence find the number of grams of copper sulfate in the tank after 6 hours. Right, so for part B, the first thing we're going to do is to rewrite this in the form that allows us to use the integrating factor to solve. So that will be dx dt. Then we bring over this term, and I'm going to write it as something times by x. So it'll be plus 3 over 100 plus tx equals 160. So the integrating factor is going to be e to the power of this. So I'll just write down if for integrating factor. So that'll be e to the power of the integral of, let's write it, put the 3 here, 3 1 over 100 plus t dt. Got a bit more space down here. So that'll be e to the 3, then it'll be log 100 plus t. Then we can bring the 3 there as a power, get the e and the log to cancel down, and we're just left with 100 plus t cubed as our integrating factor. So I'll now take every term of this and multiply it by the integrating factor. So that will give us 100 plus t all cubed dx dt plus 100 plus t all cubed times by 3 over 100 plus t x equals 100 plus t all cubed times by 160. So I need to identify my u and v. So u is always going to be here beside the dx dt, and there's my v. So that left hand side is what we get when we differentiate with respect to t, this product, 100 plus t all cubed x equal to 160 100 plus t all cubed. Next we integrate both sides with respect to t, integrate with respect to t. So what will happen is these will cancel out like this. So the left hand side is now just 100 plus t all cubed times by x, and then the right hand side, when we integrate it, so we can use the reverse chain rule, you add 1 to the power, divide by the new power, so this will become power 4, this will become power 4t, dividing by this differentiated, well that's just 1, so we'll end up with 4t bracket 100 plus t power 4. So we'll just write that down. So 4t 100 plus t power 4, then plus c. Now c is what we now need to work out. Now to work out c, it says that initially the container contains pure water. So that basically means that when T is 0, the concentration of copper sulfate is 0. Okay, so that bit was important about it containing pure water at the start. So we're going to replace this X with 0 and this T with 0. If we do that, this part here just disappears. That becomes 0, so we have 40 times by 100 to the power 4, so C will equal negative 40 times by 100 to the power 4. So that's our value of C. So adding our value of C and rearranging, we'll get X equals, so this will be 40 times by 100 plus t to the power 4, adding c, which is minus 40 times by 100 to the power 4, and I'm dividing both sides by 100 plus t cubed, so all over 100 plus t cubed. I want to find the concentration or the amount of grams of copper sulfate when T equals 6. So I've already done this. If I put T equals 6 into that equation, I'll give you my exact answer and then I'll round it to 3 significant figures. So I get 881.5228. So let's give that as 882 grams, and there's a 3 significant figure answer. So there's my answer for part B. You can see there's quite a bit we need to do in that, in part A and part B. So let's just highlight the fact that's part B, just in case. And in part C, how could we refine the model? In other words, what could we include or take away from this to make it more realistic? Now, as long as you give any sensible answer that's related to the question, you'll get the mark. So, for example, it was assumed, it says that the liquid or the copper sulfate, it says it immediately disperses into the hole. There we go. Immediately disperses throughout the tank on entry. While in reality, it doesn't immediately disperse. Okay, some of it may take a while to dissolve. So we might talk about this immediate dispersion is an issue. Yeah, it's not realistic. So we might want to take into the fact that the copper sulfate doesn't immediately disperse in the tank. That could make it more realistic. We could talk about the fact that, well, it says that it all dissolves. Does it all dissolve? It may take a time for it to dissolve. So we need to maybe talk about the fact that, you know, the copper sulfate doesn't all dissolve, some of it may sink to the bottom. There may be more concentration in different parts of the tank. So, you know, we could talk about that as well. We could also talk about the fact that this model sort of assumes that this tank is going to carry on filling forever, because there's going to get more and more liquid in it, 10 litres per hour. So, you know, we could talk about the fact that the amount of liquid that's in the tank, you know, we might say, right, this is only valid for a certain amount of time. Yeah, so here are just 3 examples, but any example or any reference to the question, so talk about the amount of liquid in the tank, talk about the concentration of liquid in the tank, talk about the fact that it's like pure water. You know, is it going to be pure? Is there going to be some remnants of copper sulfate from before? Talk about the fact that you know, it talks about how it's immediately dispersed throughout the liquid on entry. Any of these things will get you a mark. It's always worth reading through the question again and see what things are mentioned to simplify the question. Yeah, those are the types of things that you want to mention here in this part C. Any simplifications here? You should now be able to do exercise 8A on pages 174 to 175. And this is the modelling with these first order differential equations, which will normally be in this sort of form, like this, and we solve by using this integrating factor, and that integrating factor will be e to the power of that function that's next to y, or v or t or whatever it is, and then we will multiply every term by that integrating factor to allow us to solve these first order differential equations.